Hello students, welcome to the 29th lecture on particle physics, and today we shall be talking about atmospheric neutrinos and reactor antineutrinos. Now let us first discuss atmospheric neutrinos. As we know that cosmic rays are coming from all around us and bombarding the Earth's atmosphere, and these cosmic rays are nothing but particles, mainly protons and alpha particles, and very small fraction of heavy nuclei, CNO nuclei, and therefore the name cosmic ray is a misnomer. Actually, these are particles which are coming from outside the solar system, but within our galaxy, as we know that we are living in Milky Way, the name of our galaxy, or its Hindi name is Akash Ganga and Urdu name is Kehkashan. Therefore, these cosmic ray particles are bombarding to the Earth's atmosphere, and then with the air nuclei they are interacting, and with the interaction they are producing pions and kaons. These pions and kaons then travel in the atmosphere, and these particles are short-lived particles. Therefore, they decay. They decay mainly to neutrinos, and thus this constitutes atmospheric neutrinos. Now, the low energy neutrinos are mainly coming from pions, while very high energy neutrinos, they are coming from the kaons that we shall talk about. As we know that when pions become highly relativistic, they won't decay because of the Einstein's special theory of relativity. Because of the length contraction, they will come to the earth, while kaons mass is 490 MeV approximately, and therefore they will be able to reach to they will be able to decay, and the neutrinos hence will be produced from these kaon sources. Now the important point is that these neutrinos have been observed in the experiments, and this is what I am showing you, that there are these white arrow is showing the primary cosmic ray particle is interacting with air nuclei, and then you have pions and kaons, and these pions and kaons are then decaying into muon and neutrinos. Pi plus is giving nu mu and pi minus is giving nu mu bar, and then mu plus minus also is has got a definite lifetime. While it progresses, it decays to electron, mu minus decays to electron, antineutrino, and nu mu. Mu plus decays to E plus, nu E, and nu mu bar. Therefore, the general expectation is that we will have two muon type neutrinos and one electron type neutrino. And therefore, if we talk about the ratio of these two neutrinos, muon type to electron type, this should turn out to be equal to 2. This is the naive expectation from the general concept that protons are interacting with the Earth's atmosphere, they are producing pions and kaons, and these pions and kaons, they are decaying to muons and neutrinos, and muons and then decaying into electrons and electron type neutrino or antineutrino, and muon type neutrino and antineutrino, as have been shown here in the reaction. Now, the different experiments have measured this muon to electron neutrino flux, and they have found out that instead of 2, this ratio is 1 or 1.2, and this means that there is a discrepancy between the theoretical prediction and the experimental observation. And this difference is known as atmospheric neutrino anomaly in the literature. Now, several experiments have been performed, and it was well established by Super Kamiokande collaboration in the experiments performed in 1990s and after that really there is a neutrino oscillation. And if we consider neutrino oscillation as we discussed in the case of solar neutrinos, here also neutrinos are changing flavor, and that is why this ratio, instead of being 2, it is becoming smaller than 2 and closer to 1. Now, when we talk about primary cosmic rays, then these primary cosmic rays, they don't have unique energy. The spectrum is quite broad, and as you can see that you have primary cosmic rays of energy up to 10 power 20 electron volts or more than that. And therefore, in earlier days, when we don't had accelerators, balloon experiments were performed using cosmic ray particles. And that is why cosmic rays are also known as Boltzmann accelerator. For example, in India, we don't have a neutrino laboratory currently. We are striving to have one, or we don't have particle accelerators as these are very costly, but experiments have been performed using cosmic rays starting in 50s and 60s. Therefore, these cosmic rays are the particles coming from outside the solar system but within our galaxy mainly. But what is the source of those cosmic rays, protons and alpha particles, which are known as the primary cosmic rays, still we don't know. That is still a topic of research. While the pions and kaons, they are known as secondary cosmic ray particles. Now, there is an important concept when we talk about these cosmic ray particles, that we know that our Earth is a magnet, and it has also North Pole and a South Pole, like geographical North and geographical South, except that the case is that if we consider this to be a sphere, and this is the geographical North and this is the geographical South, then magnetic South is near to the geographical North and magnetic North is nearby geographical South. And that is why when we put a magnetic needle, the magnetic needle shows the direction of north and south, opposite poles attract, and this magnetic needle's north is closer to the geographical north, and that is why we say that magnetic needle shows us the direction of north or south, etc. But the important point is, since when we are saying that Earth is a magnet, then for sure there are magnetic lines of forces. And when we are talking about magnetic lines of forces, then primary cosmic rays, which are coming in the direction of the equatorial plane of the magnet, then they will feel the Lorentz force and they can be repelled back, or they can change its direction, while the cosmic rays which are coming towards the pole, they won't feel such type of force. And that is why we talk about magnetic effect on the cosmic rays. In turn, that effects results in the neutrino flux also, because those who are turning back those particles won't give rise to neutrinos. Therefore, we have such type of effect that has been studied in nature. Therefore, what we are talking about, that we have primary cosmic ray particles. They are giving secondary cosmic rays, mainly pions for the low energies and kaons for the high energies. And then pions are decaying to muon and neutrinos, and we have two muon type neutrinos should be there if we are talking about one electron type neutrino. But this has not been observed. As we are showing here, this number is almost equal. Now, theorists have obtained or predicted the neutrino fluxes at various sites around the globe. For example, here it has been shown for Kamiokande site, INO site. INO is a proposed India-based neutrino observatory experiment. Kamiokande is a experiment in Japan. SPL stands for South Pole Experiment, and PYH stands for an experiment which is being performed in Finland, Shalmi. Therefore, these are the various neutrino experiments. These are the different neutrino fluxes which have been predicted by the theoretical models, and they are basically the predictions. And as you can see, these fluxes are different for the different neutrinos. Their energies are also slightly different, and then they vary from a few GeV to up to 10,000 of GeVs. Then what has been observed, that there is a seasonal effect also. When it is hot, Earth is rarer, then the interaction would be different. When there is winter, there is a dense atmosphere, then there will be more interaction, and therefore you will observe the different neutrinos in these seasons. Therefore, these are showing the neutrino predictions from June to August or December to February, winter season, and then the average, etc. Now, as I have told you, atmospheric neutrino experiments have been earlier performed at Kamiokande, by the Irvine, Michigan, Brookhaven collaborations in United States. It is being performed at South Pole. The name of the experiment is Ice Cube. Then Minos, Super Kamiokande, the experiment is still going on. Then INO is the planned experiment in Tamil Nadu. Then let us talk about the reactor antineutrinos. We have discussed in one of the lectures that this radioactive decay of the nucleus, or like uranium or thorium, they give rise to neutrinos. And that means all the nuclear power plants are the sources of antineutrinos. If you can recall, then for the very first time when neutrinos were observed by Rines and Cohn in 1956, it was at Savannah Nuclear Reactor Power Plant, and that was also antineutrinos. Therefore, historically also, for the first time, the neutrinos which we call that we have discovered them in 1956, it was really antineutrinos. Then solar neutrinos were observed by Davis and collaborators, which we have discussed on the last turn. It was antineutrino, therefore, which was detected for the first time in 1956 by Rines and Cohn. And since then, the reactor antineutrinos have played an important role in both the discovery as well as in the precision measurements of the neutrino oscillation parameters, which we will talk about. What is neutrino oscillation, and what are the different parameters, and how are they determined, and why are they important. The isotope rich in neutrons like uranium-235, uranium-238, plutonium 239, plutonium 241, through the fission process within the power reactors, undergo a series of decays, which may be broadly represented by the reaction a radioactive nucleus is decaying into a daughter nucleus. Besides that, electron and antineutrino are being produced. Now, the mixture of the isotopes produced is complex. It is not solely one entity, which results into a continuous energy spectrum of electron type antineutrinos with energies ranging from 0 to approximately up to 8 MeV. And the average energy is around 2 to 3 million electron volts, along with the emission of 200 MeV of fission energy. Therefore, in each fission reaction, we have 200 MeV of energy. Therefore, you can see that when neutrons are bombarded on these radioactive nuclei, we have the daughter nuclei, more neutrons, and this much amount of energy. Now, the important point, as you can see, that on the right hand side, the daughter nuclei are not the same, and the number of neutrons also, those are released, they are not the same, and that is why the energy released in fission reaction is not unique, and that means we are talking about a continuous energy spectrum. The other important point is, yesterday I have told you that in general you take 2 protons and 2 neutrons individually, then mass of these 2 protons, 2 neutrons are not equal to the mass of alpha particle. Rather, they weigh more than the mass of the alpha particle, and the difference in mass comes out in the form of energy. Similarly, for the heavy nucleus, this mass of a heavy nucleus, the nucleons inside them, is more than the mass of these nucleons in these daughter nuclei, and this difference in mass also is coming out in the form of energy. Therefore, we have discussed this about mass per nucleon versus atomic number. Now, in nuclear reactor is the strongest terrestrial antineutrino source coming from the beta decays of unstable nucleus, and one fission reaction yields about 200 million electron volts of energy, and simultaneously it releases about 6 antineutrinos on the average. Therefore, in one fission reaction, 200 MeV of energy gets released, and it also gives rise to 6 antineutrinos. Now, what we know that from here, that 1 watt will be equivalent to 3 into 10 power 10 fission reaction per second. And if we are talking about 200 megawatt of power plant, then that means that will give rise to 2 into 10 power 11 antineutrinos per second. This is because 200 MeV will be equal to 200 into 10 power 6 into 1.6 into 10 power minus 19 joules, and that would be equal to 3.2 into 10 power minus 10 joules. And since we know that we are talking about 1 watt, and that means this much amount of energy joule per second, and that means if we are talking about 200 megawatt of power plant, that means 10 power 8, sorry, this will be mega is there, therefore this will be 10 power 6, 200 10 power 6 joules of energy in one fission from a power reactor. Then what we are saying that in one fission reaction, this much amount of energy is released. In one fission reaction, what we say that 3.2 into 10 power minus 10 joules of energy is getting released in one fission reaction. Then to have 10 power 2 into 10 power 8 joule of energy per second, how many fission reactions we require? We require around 10 power 18 fission reaction. And this would imply that, as I have told you, 1 watt is 3 into 10 power 10 fission per second. Therefore, 200 megawatt will give rise to 2 into 10 power 11 antineutrinos per second. Now, different experiments have been performed using nuclear power plant, and as you can see that if I am telling you that this is my nuclear reactor and I am in a city which is say 10 kilometers from here, then again I can put a sphere and I can write 10 power 11 upon 4 pi r square. I can from here tell you that how many antineutrinos per centimeter square per second are reaching to us. Therefore, everywhere where you talk about, if you have got a nuclear reactor power plants and you are staying at a distance of 10 kilometers, 100 kilometers, so gradually this is following inverse square law, therefore the intensity will fall. But you can tell yourself that how many antineutrinos are being produced. Now, what I am telling you, that these radioactive sources like uranium-238, uranium-235, plutonium-239, their antineutrino spectrum is not unique. Broadly, they lie between 2 MeV and 8 MeV. But if we look at their curves, flux curves versus energy, we find that there is some difference. Therefore, the detectors are made which are sensitive to these low energy neutrinos. Now let me come to geoneutrinos. What are geoneutrinos? As we know that in our Earth's core, the temperature is very high. There are molten ions. There are radioactive nuclei. And that is why one theory is that these ions, since our Earth is rotating, therefore these ions are in motion, and this motion of charged particle with time should give rise to a current, and associated with current there is a magnetic field. Therefore, geoneutrinos are coming out from the core of the Earth, and this is because of the radioactive nuclei present inside the core of the Earth, and there the temperature is very high. Now, Earth gives around 31 terawatt of energy. Almost half of this heat is re-radiated energy from the sun, and the other half that we are talking about is produced from the Earth's interior. The Earth contains certain amount of radioactivity, but how much it accounts has been difficult to say. And that is why, since we know that the radius of Earth is 6,400 kilometers, this Earth is 6,400 kilometers. And till now, humans have digged only up to 15 kilometers. Therefore, it is impossible to think of digging up to or reaching to the core of the Earth in the next 1,000 years. But if we want to know something about the Earth's core, these antineutrinos can be the best source. And in fact, at Camland, these antineutrinos have been observed, and these antineutrinos are coming from the core of the earth. Now the amount of antineutrinos that you have observed on the surface of earth, those are coming from the core, originating from the core of the earth, that can tell you what is the concentration of those radioactive nuclei inside the core of the earth. Therefore, the concentration of this radioactive nuclei or the composition of the matter inside the core of the earth can be best told by these reactor antineutrinos. That is why experiments are going on to study these antineutrinos. Mainly, these antineutrinos are produced via radioactivity decay of uranium, thorium, 40 potassium, etc. in the Earth's core, and the flux at Earth's surface is around million antineutrinos per centimeter square per second, because these are radioactive nuclei, and radioactive nuclei are the sources of antineutrinos. That is why, like reactor, here also we are talking about antineutrinos, and the flux on the surface of the earth is expected to be around 10⁶ per centimeter square per second from the known sources that we have information that constitutes the Earth's core. But if we someday observe a much different value from this theoretical from the other results, then for sure we will have to think of the other materials, those are present inside the core of the earth, or the concentration of the material inside the core of the earth. That is why I am telling you that these antineutrinos can carry information about the spatial distribution of radionuclides. This is what I am telling you, that these are the nuclei that one thinks is there inside the core of the earth. They are radioactive nuclei. They are giving rise to antineutrinos, and these antineutrinos are coming to us. Now let's just stop here, and in the next lecture we are going to talk about another fascinating topic, and that is on relic neutrinos. See you next time. Thank you very much.